Okay, let's solve the problem about Hancock and the train. So what we have in this situation is that Hancock is at rest and then this train is coming, and how do we calculate what's the time that it needs to stop the train or the distance? Well, we have to do estimates first, and we can estimate that the mass of Hancock, reasonable number, is 90 kilograms. The mass of the train, you can just Google what's a reasonable number for that, and I just pull up a not too big number, just to be conservative, 50 tons, 50,000 kilograms. The velocity, let's say it's about 40 kilometers per hour, which if you go from kilometers to meters and hours to seconds, so this is a second, sorry, you get 11 meters per second. And let's be generous. Let's say that the friction coefficient is 1 for the static and 1 for the kinetic, just to be very, very conservative, just to try to explain what we see in this scene. The first thing is, okay, we have a collision between a train and Hancock, so there are forces there. We need to do the free body diagram, which will be this one. So we have here Hancock, and there will be a force from the train and friction. Let's apply Newton's second law here. That will be for Hancock, the horizontal one. We know that in the vertical one we have that the normal is equal to mg. There is no acceleration or motion in that direction. And in the x-axis, I just wrote that there is an acceleration. We will talk about if there is acceleration or not later. Now, what I want to calculate first is what would it have to be the friction coefficient in order for this scene to be correct. We know that friction only depends on the mass of Hancock and the friction coefficient. If we assume that his mass is 90 degrees, what is the friction coefficient that allows this scene? Okay, I'm going to solve this equation, Newton's second law equation, and solve it for friction coefficient to see if it makes sense, if it's reasonable or not. So, because of Newton's third law, the same force that the train does on Hancock is the same force as Hancock does on a train. So let's write the equation for the train. We see in the scene that he kind of like stands there and the train stops in about 1 second, let's say. So if it's 1 second, we can calculate that acceleration because it goes from 11 meters per second to 0 in about 1 second. Once we have the acceleration, we substitute here. And we get 5.5 times 10 to the 5 newtons, 55,000 newtons. Okay, that's the force that Hancock does on a train, which is the same as the train does on Hancock. So let's get that number. Come here to the equation of Newton's second law on Hancock, and let's solve it for friction force, and then once we have friction force, we will calculate mu. Once we get this number, because this, we get that mu is approximately 623, which we don't find in nature anything like that. So that doesn't make sense at all. We cannot see that scene. Okay, now that we know that that scene is not correct, let's try to describe the correct scene. Assuming that Hancock is very strong and he is not going to suffer any damage because of that accident. Now we are going to calculate, assuming mu equal to 1, we are going to calculate without friction what's the distance and the time required for the train to stop. So what we have here now is, this is Newton's second law, the first one applied on Hancock, the second one applied on the train. We know that the force acting on Hancock minus friction on his feet is equal to his mass times acceleration. And on the train, exactly the same force, because of Newton's third law, is equal to the mass of the train times the acceleration. Because those two masses are the same, two forces are the same one, we substitute this force in here and we can solve for the acceleration. Just from the definition of friction. And assuming now that mu is equal to 1, it's an acceleration extremely small, 0.018 meters per second, so that's like about 2 centimeters per second squared. That's really slow acceleration. Of course, that's because the train has a large mass and a reasonable velocity. So this is the acceleration. Let's calculate what's the distance. To do that, we will use the kinematics equations that relates velocity with distance and acceleration. We just substitute here. Which is more than 3.3 kilometers. That's a lot. Now if we want to calculate the time, we again use another of the kinematics equations. We are assuming that the acceleration is constant. And that's about 10 minutes. Now I want you to watch this Indiana Jones scene again and estimate what is the energy dissipated by friction .
Water! Water! Water!
Oh, look!
Water!